The objective of this lab was to build an induction furnace that could be operated safely. To do this, we will need to identify hazards and develop and use safety procedures. Safety hazards include high temperatures and high currents. Our safety system is called lockout-tagout, which we will now demonstrate.
So this is our lockout-tagout mechanism. What we did here is we took a power cord which ran to our power supply and spliced it, then inserting a switch. From the switch, as you can see, there's this plastic cover piece on it, which then has this metal clamp, which is the lockout-tagout.
When we are ready to power the system, the locks are then removed.
The clamp is then separated, allowing us to open up the plastic piece. Then giving us access to the switch, and the Bert will flip the switch, which then powers the system.
Now that our safety system has been covered, it is on to the driving force behind the induction furnace. Heating is made possible by electromagnetic induction. By exposing a workpiece, shown in blue, to changing magnetic fields, a potential difference is induced inside the workpiece. This induces currents in the workpiece, called eddy currents. If the eddy currents are great enough, they can cause a change in temperature of the workpiece. The heating of the object occurs because of Joule heating, also referred to as ohmic or resistive heating. The amount of heat is proportional to the current squared times the resistance, given by Joule's first law. Let's take a quick look at the schematic. We've split the system here into 3 separate subsystems. Subsystem 1 is the portion that is responsible for making the tank circuit current alternate. The MOSFETs alternately ground a side of the main coil, causing the current to constantly change direction. By applying a changing current to the tank circuit, the generated magnetic field inside the inductor will be constantly changing. Subsystem 2 is the section containing the resonance circuit. The tank is made up of an inductor and a capacitor. The capacitor stores its energy in an electric field, while the inductor stores its energy in a magnetic field. As the capacitor discharges, current flows through the inductor, building a magnetic field. When the capacitor's charge is 0, the magnetic field will collapse, and the current will reverse. The oscillation of energy from the capacitor's electric field to the inductor's magnetic field is called resonance. Subsystem 3 is our safety subsystem. It includes the lockout-tagout system and an inductor used as a choke. The choke inductor is in place to both prevent high-frequency oscillations from entering the power supply and to limit the current. Now let's take a look at the physical setup.
Our circuit required resistance value of 250 ohms. So we put 4 1K ohms in parallel, as shown right here. And then next we needed 2 Schottky diodes. One's right here and the other right there. And then we had 2 MOSFETs right here, and we put heat sinks on them to help dissipate the heat. And we supplied this board with 15 volts. These are 0.1 microfarad capacitors that we use in our circuit. There were originally 10 of these in parallel, but to increase the resonant frequency of our system, we cut off until we got to about 4. This is how the capacitors were soldered on to 14 gauge copper wire, which is connected to our inductor coil. This is our inductor coil. It consists of 14 gauge copper wire. We wrapped the copper wire around a 1 diameter PVC pipe, and we did this twice, and we soldered it together to make it center tapped for a total length of 6 inches. This is our choke inductor, which has about 160 turns of 22 gauge wire.
Now it's time to combine all the components and put everything together.
Okay, so what we're doing now is actually setting up our system. We're going to mount our coil piece, which is connected to the capacitors here in this joint, which is going to keep our coil lifted in the air so that it does not heat or burn anything. From there, we're going to move on over to the actual circuit, which we're going to take alligator clips, which we're running from our MOSFETs to heat up, or to the actual coil. From there, we're going to use our wires coming out of our power supplies, and we're going to hook them up to the circuit. From this power supply, we're going to be running 15 volts into the actual breadboard. We have also grounded it.
It is now time to activate the circuit. Remember, be alert, don't get hurt. Follow all the safety precautions.
So now we're going to address our safety issues by all of us putting on our safety goggles. Now that all group members have verified that the circuit is correctly set up and are ready to power it, we will now remove our locks from our lockout-tagout mechanism. We will remove the clamp, giving us access to the switch. Flick the switch on, then power in the circuit. Move over here and turn on both our power supplies. As you can see, it's at 15 volts. And that's at 15 volts as well.
The current rises as the workpiece is moved further into the coil.
So now we will enter our steel rod into the coil, which will be heated. Just in there. Now you can see on here we're drawing almost 4 amps. So as you can see, the temperature is rising with the time.
We can alter the frequency by changing the capacitance. This first equation is what we used to find our inductance, as we have an air coil inductor. We use this to find our theoretical value of inductance. To find capacitance, we simply multiply the value of one capacitor by the number of capacitors, as they are in parallel and they all have the same value. The next line contains the reactance for both inductors and capacitors. Resonant frequency occurs when the reactances of these are equal in magnitude. Setting these equations equal to each other, you can get a formula to find the resonant frequency based on inductance and capacitance. If we keep the inductance constant, you can see that by lowering the capacitance, we can raise the frequency. To obtain the theoretical frequencies, we use the formula above. To obtain the actual frequencies, we used a differential measurement, with one oscope probe at the top of the coil and the other oscope probe at the bottom of the coil. Starting from 10 capacitors and decreasing to 4, one by one you can see the change in frequency as each capacitor is removed. We can make this furnace more powerful, but we need to take a few things into consideration. If we want to push larger currents for larger amounts of time, we will need a type of coolant system for the coil itself. Diodes would also need to be changed out for ones rated for a higher voltage. Changing the power supply to one that can provide a higher current would also help. You'd also need different capacitors with higher current and frequency ratings.